Hello, my name is George Karipis, and I'm a Senior Principal Scientist at AWS AI/ML. What I will be covering today is the DeepGraph Library, an open source technology that we're developing at AWS for solving large machine learning problems involving graphs using graph neural networks. The agenda is as follows. I will start by showing you how extensive are the applications of graph learning and describe the types of machine learning problems that graph learning is designed to solve. I will then provide an overview of graph neural networks and discuss the advantages, then continue by providing an overview of DGL, and conclude by describing how we are scaling DGL to very large graphs. In order to see how graph and where graph learning is applied, let's look at some example problems. The first problem that I would like us to focus on is that of developing a machine learning method to predict if a particular user will like a particular show. Will Shinu like Goliath? The standard way of solving this problem is to combine the features of the user, for example, various demographic information as well as information about the device that the user is using, along with the features of the show, for example, the storyline or the genre or any keywords associated with the plot, and train a model to predict the rating. However, this approach misses out on the fact that the underlying data forms a graph. In its simplest form, this is a bipartite graph containing two sets of nodes, users and shows, whose edges indicate which shows each user has rated in the past. Having access to this graph, I can expand the information that I take into account when predicting how Shinu will rate Goliath. For example, Goliath was rated by Alice and Vega, and Shinu has also rated other shows that those two have rated, Hannah and Marvelous Miss Maisel. A machine learning method can potentially use this information to obtain more accurate predictions. Moreover, this graph can be augmented with additional information, for example, a social network among users or a show knowledge graph, which can further boost the performance of the machine learning methods. As a second example, let's consider the problem of detecting a fraudulent user. In a mobile shopping app, in building a machine learning model for that, I can take into account information about the customer's past transactions and their characteristics. For instance, what credit card they used, what devices they used, and in which locations they made those purchases. However, the accuracy of the machine learning model can be substantially improved by taking into account the network formed by the transactions of all the users in the system. The fact that the user in question shares the same credit card with another user that committed fraud is a strong indication that the user in question is also a fraudulent user. Machine learning algorithms that take the graph into account can achieve higher accuracy. As another problem, let's consider the task of trying to decide which drug to use for a new disease. Some of you may remember the announcement back in June of 2020 about dexamethasone, which was one of the first widely available and cheap treatments of COVID-19. The problem that I would like us to focus on is how can I develop a machine learning method to predict which of the existing drugs can treat a new or existing disease. In order to find such drug, I can pursue various routes. First, I can find similar diseases to the disease at hand, for instance, diseases that are similar to COVID-19, and then see which are the drugs that are used to treat those diseases, and those can become candidate drugs. Or I can find proteins that are similar to the proteins responsible for the disease, and then see which of the existing drugs bind to those proteins, or bind to proteins that regulate them, or are part of the same biological pathway. All this prior knowledge is often encoded in the form of a knowledge graph, which I can then apply machine learning approaches on it to find if dexamethasone is a potential treatment for COVID-19. At AWS, we did something like that, and we released a knowledge graph for drug repurposing applications by combining information from different databases. We went one step further and applied machine learning approaches on the knowledge graph, similar to the approaches I will be describing later, and we found that they are quite effective in identifying drugs that were investigated for possible treatments for COVID-19. So in fact, a study that we did back in early June, we found that dexamethasone was ranked number 4 among the 100 highest ranked drugs according to the method that we developed. To summarize, what we see is that the underlying data in all of these problems are linked together via graphs, and all these problems can be solved by using machine learning approaches based on graph learning. What are the problems that graph learning solves? Well, it solves 3 broad categories of problems. The first category involves problems that have to do with predicting something about the nodes in the graph. For example, predicting whether a particular customer is a fraudulent user or not is one of those examples of a node prediction task. The second task that graph learning problems solve is to predict something for the edges of the graphs. For example, predicting the rating that a user will provide to a show or a movie is one of such tasks. Or predict whether or not a particular drug will treat a particular disease is also an edge-level prediction task. And the third task is what's called the graph-level prediction task. So those are and for this particular task, we haven't seen an example, but a prototypical example for that will be determining whether or not a particular compound will bind to a particular protein or not. So the entity that we're trying to predict something for here is really a compound, and that compound is often represented via its molecular graph. And what we want to do is we want to be able to predict something for the entire graph. So note that the edge level predictions, so note both the node level, edge level, as well as graph level predictions can be either classification tasks or regression tasks. And the edge level prediction task, quite often is also called, link prediction task. A common way to solve these various graph learning problems is to embed the nodes of the graph to a low-dimensional space and use these embeddings to train off-the-shelf classifiers. This approach works well as long as these embeddings capture essential task-specific information. For example, nodes that are similar in the embedding space are also nearby in the original graph. A number of different approaches have to be developed for computing these embeddings that broadly fall into 2 categories. So the first class generate these embeddings using various manual feature engineering approaches. So these approaches require domain expertise, involve considerable amount of fine-tuning, and they are time-consuming and do not scale. To address some of those limitations, the second class of approaches rely on automatic methods that use various self-supervised dimensionality reduction techniques. So techniques that fall into this category are singular value decomposition, tensor decomposition, cofactorization, deep walks, and others. So even though these approaches address some of the shortcomings of the manual feature engineering approaches, they have their own drawbacks. One is that they cannot effectively combine rich attributes along with the structure of the network. The second one is they employ mostly linear or multilinear models, and that they are quite shallow. So then the question that arises is, can we do better than that? And the answer to that is yes. And this is what GNNs are designed to do. So graph neural networks is a family of deep neural network models that learn node, edge, and graph embeddings. To compute an embedding of a graph, a GNN looks at the subgraph around each node. For example, looking at that red node over here, in order for a GNN to compute an embedding, it's going to look at that node's ego network, which is defined as the subgraph around that node that is up to k hops away from the target node. Okay? In this particular picture, what we have k equal 2. So given the ego network of a node, the GNN uses a function to compute an embedding for the target node by using the information in that ego network. That information includes both the structure of the ego network, that is its topology, and also the features of the ego network's nodes and edges. This function, which is often called the encoder, is learnable and is learned in an end-to-end fashion. Some of the early GNN research started about 7 to 8 years ago. In the past few years, GNNs have taken off. GNNs have become one of the hottest areas of deep learning research today. And the reason for that is because they are able to achieve state-of-the-art performance for solving problems in a large number of domains. Though there are several graph neural network formulations, the most common one is based on the message passing model. The idea is that nodes send messages to the adjacent nodes, and each node aggregates all the messages it receives from each of the nodes and uses those messages to update its representation. In this particular figure, what our goal is to update the representation for node V1, and during the message passing paradigm, nodes V2, V3, V4, and V5 send a message to V1. V1 receives those messages, and then it applies a function to update its representation. So mathematically, this is expressed as follows, in which this corresponds to which messages are sent to the target node, and the target nodes combine. Those messages are aggregated, and then they're used to update the representation. The message and update functions, so M superscript L and U superscript L, are learnable, whereas the form of the aggregation function is not, and is part of the GNN model design. So besides summation that is shown over here, you can have other associative operations such as minimum, maximum, and products. So the set of operations composed of message passing, aggregation, and update correspond to a layer of the graph neural network. Multiple such layers can be stacked one on top of the other to allow the representation to capture information from nodes that are multiple hops away. For example, if I stack 2 layers of the GNN aggregate message passing, then I will be able to incorporate in V1's representation information from neighbors that they're 2 hops away. To make things concrete, let me give you some examples of 2 actual GNN models to see how the message passing and update functions work. One of the simplest and yet quite effective GNN model is the graph convolution network. In the graph convolution network, or GCN in short, each layer of the GNN model updates the representation of a node by first averaging the representation of its neighbors, including itself, multiplying by a layer-specific learnable weight matrix, and applying a dimension-wise nonlinear function, for example, ReLU. Note that these equations are applied to each node in the graph, and after each layer, the representation of a node now includes information from the nodes that are 1 hop further away. Note that in the first layer of a GCN, the representations that are used as input during the message passing depends on the node's features, and by using these features is how a graph neural network model is able to capture embeddings that capture information both about the feature of the nodes and also about the topology of the graph. So the second model I would like us to cover is the relational graph convolution network, and it's designed for graphs that they are heterogeneous. A heterogeneous graph is a graph whose nodes and edges are of different type. A prototypical example of such heterogeneous graph are knowledge graphs. In this particular example, it's a knowledge graph about artists in a ballet, in which we have information about countries of origin, information about the name of the person, information about the word, as well as the relations indicated, information about, where they educated, where their work took place, what were the cities and their off, and so forth. The relational graph convolution model is an extension of the GCN model that performs the aggregation in 2 steps. First, it aggregates a representation of the node's neighbors that are connected by the same relation type. Second, it aggregates these relation-specific aggregates. In terms of model parameters, besides the weight metrics associated with the update operation, which is similar to the one used in the GCN, the relational GCN also has a relation-specific weight matrix, which is used to learn the importance of each particular relation type. So one of the drawbacks of GNNs over traditional approaches is that they require more computations. So this becomes even more critical when the application involves large graphs. For example, large social graphs or applications in large-scale recommended systems, or dealing with extremely large knowledge graphs, especially knowledge graph that has to do with common knowledge. So the way GNN solved that problem is by adopting a training approach called mini-batch training. So in mini-batch training, we randomly select a small number of target nodes to form the mini-batch. For each target node, we extract its ego network and structure the required computations in the form of a tree. So that tree is the computational graph that is associated with the target node. So in this particular picture on the right, we see the computational graph associated with target node 1 for applying a two-layer GNN. You can see that the final representation of node 1 will become as a result of the second layer of the GNN. And in order for that second layer representation to be computed, node 1 needs to receive messages from its neighbors, nodes 2, 3, 4, 5, and 6. And those are the messages that corresponds to their representation that comes as a result of the first layer of the GNN. Now, in order to compute the representation of those nodes, 2, 3, 4, 5, and 6, at the end of the first layer of the GNN, they need to receive the representations of their neighbors from the initial input features. So this structure leads to the tree-like structure that you see on the right, and for which the input features of the lower level are propagated to compute the representation of the nodes on the middle level corresponding to the output of the first layer, and the features of the output of the first layer are used to compute the representation of node 1 at the end of the second layer. So the union of these computations, so what you see over here is the computation associated with a single target node. So the union of those computations over all the nodes that form up the mini-batch are the set of computations that are performed during mini-batch training. And as long as the number of nodes involved in these computations can fit into the memory of a GPU, those computations can be done efficiently. However, this may not always be feasible to feed all the data from a mini-batch into the GPU memory. And this is particularly true for graphs that correspond to small world graphs. Those are the type of graphs in which most pairs of nodes are connected via a short length path. So what happens in those small world graphs is when I create a mini-batch, then that mini-batch will end up having a large fraction of the number of nodes in the overall graph, and hence not allowing me to store everything into the GPU memory. So in order to solve that problem, what GNNs use is to do a neighbor sampling. And the idea of neighbor sampling is, instead of using the entire ego network to form the computational graph, they only sample a small number of the nodes in that ego network. And the way that thing is done is usually by putting an upper bound on the number of neighbors to sample. So this allows the computational graph to be of bounded size, and hence we can use that thing to scale to graphs that have a power law degree distributions. Okay, now I would like to switch gears and give you an overview of the Deep Graph library. But before doing that, I would like to answer the question that many of you may be asking is, why do I need something special for GNNs? And the reason for that is because there are already a large number of deep learning frameworks, such as PyTorch, MXNet, and TensorFlow, that I can use to train neural network models. So the answer to that is because the existing deep learning frameworks optimize for workloads whose computational graphs are fixed and for calculations involving dense tensors. Okay, both of those do not hold for GNNs. So recall from the previous discussion of mini-batch training that what we see here on the left is a computational graph associated with node 1. The computational graph for node 2 will be different, as it will depend on its own ego network, and the same will hold for node 3, nodes 4, and so on. So this different computational graphs are something that existing deep learning frameworks cannot handle. Moreover, if I'm going to employ neighbor sampling, now the computational graph associated with node 1 will be different from epoch to epoch because every time I'll be sampling a different ego network. So because of those limitations, then something needs to be done to be able to deal with GNN efficiently computationally. And this is what led to the development of the Deep Graph Library. So development of DGL started in the middle of 2018. And the first release was done during NeurIPS 2018. Since then, it has been under active development, with the most recent release is version 0.6 that took place a couple months ago. So DGL sits on top of any one of the existing deep learning frameworks, such as PyTorch, MXNet, and TensorFlow. It implements highly optimized sparse graph operators in C++ and provides user-friendly Python APIs for GNN-related operators. In addition, DGL provides some domain-specific packages, such as DGL Life Science and DGL KG, that contains models for computing embeddings for knowledge graphs and solving various problems in drug discovery. So the graph class is at the core of DGL's programming interface and provides an easy, consistent way to access the graph's data and express the desired computations. Similarly, it provides versatile APIs for all of the GNN operations. For example, in DGL, you can use a single call called updateAll to perform the message passing and update operations. In that call, you provide the message passing function, the aggregation function, and the update functions as either user-defined functions or built-in functions, and that allows you to express all the computations in just a single API call. DGL provides an extensive API for manipulating the graph, expressing the GNN model's message passing steps, and performing the operations required to scale training to large graphs. In addition, it provides several built-in NN modules for common GNN layers and various datasets to speed up development and testing. It comes with an extensive documentation and tutorials to get you started in developing and using GNN models. As a last item, I would like to spend a couple of slides describing DGL's distributed training design and performance, which allows it to scale to graphs with billions of edges. Since the 0.5 version of DGL, it has provided support for distributed training. This support is continuously being developed and expanded, and in the most recent version release of DGL, 0.6, it provides support for distributed training of heterogeneous graph. So DGL provides a full distributed design where all the computations performed during GNN training are parallelized across the machines. So the way it achieves it is by partitioning the graph across the machines. In order to reduce the amount of communication that is performed, and collocates the data with computations. It adopts a data parallel way of doing mini-batch training and uses a synchronous approach to update the GNN's model parameters that ensures that the model converges to the same quality as the non-distributed counterpart. And then to ensure that the updating of the embeddings, the sparse updating of the embeddings, does not lead to synchronization overheads, it adopts an asynchronous approach of doing that update. As a result of all these optimizations, DGL distributed training is able to achieve near linear scalability. It's able to achieve a speed up of 15.3 on 16 machines, without degradation in model accuracy, on a graph that has, 110 million nodes and 3.2 billion edges. And it can train graphs of that size on 16 machines in just a few minutes. Moreover, the accuracy of the performance obtained of the resulting model does not degrade at all compared to the non-distributed version counterpart. Finally, I would like to conclude by reiterating that DGL is an open source software effort that is being led by AWS. It is very successful, with over 7.2 thousand GitHub stars and 1.5 thousand forks. It has a vibrant user community, that spans the entire globe. It has many active contributors, including some of the leading chip companies, such as Intel and NVIDIA, that they are working with us and are contributing key performance optimizations so that DGL runs efficiently on their respective hardware. So if you want to learn more about ML and other AWS training, you can follow the links here. And that concludes my talk. Thank you.